Hello, welcome to section 5.3. We're going to be identifying similar triangles. Alright, so this problem says, through the use of geometry and similar triangle knowledge, we can find the height of objects that can normally not be measured. Suppose you want to know the height of the flagpole in front of Prospect High School. The sun's shining on you and the flagpole, what it's going to do is create similar triangles. Alright, so for this first example, we have this situation where here you are standing with your wagon full of books, ready to learn your geometry, and it says that you are 5 feet 6 inches tall and your shadow is 6 feet 6 inches long. The flagpole in front of Prospect High School, who someone's running up to, put the flag up there, is casting a shadow that's 125 feet long. Ignore the wacko running up. No, I'm not going to ignore him. He's the best part of this problem. So the first thing that kind of, stands out to me is that your measurements are in two different units. We have feet and inches for both your height and the shadow's length. The flagpole, they only gave me the length in feet. So when I do these problems, I do have to convert and have all the same units. So should I convert all of these measures to inches or should I convert all of them to feet? You can do either one. However, there is an easier way to do this. There's a faster way, and that is to convert everything to feet. All right, so the first thing we're going to do is draw the situation that we have here. We have you and your shadow, so this is you. Then we have the flagpole and its shadow, because we could actually measure these distances. We know how tall we are. We know how long our shadow is. We can go over here, take a measuring tape and measure that shadow. It would be really difficult. Yes, this man happens to know how to run up a flagpole, but that's not typical, right? So you would not be able to take a measuring tape and send him up there to measure the height of the flagpole. So we're going to use not special right triangles, similar triangles, sorry. So if you're 5 feet 6 inches tall, a big mistake that students make is they'll write that as 5.6 feet. That is not true, right? Because 12 inches is equal to 1 foot. Therefore, 6 inches is going to be half a foot. So this person is 5.5 feet tall. His shadow, which is 6 feet 6 inches, that is the same thing as 6.5 feet. So I could put the units there even so I could see that that's what I'm doing. The flagpole shadow is 125 feet. So these are similar triangles because they both have the right angle, and then the angle of elevation to the sun is the same. So therefore, by AA, these triangles are similar, right? By AA similarity, triangles are similar. So let's set up a proportion. There are multiple ways I could set up this proportion, but I have to stay consistent, okay? Consistency is the key. So the thing that I'm looking for here is the height of the flagpole, so let's call that X. So now I could do 5.5, the height of the human over the length of the human's shadow equals the height of the flagpole over the flagpole's shadow. I could have switched this. I could have done 5.5, the height of the human, over X, the height of the flagpole. But then I have to stay consistent. If my numerator is human lengths, I would have to put 6.5 over 125. Now when we cross multiply, you would see it wouldn't matter. In fact, I'm going to write that really quick. If I did 5.5 over X and set that equal to 6.5 over 125, notice that when I cross multiply, here I'd have 6.5x, here I'd have 6.5x. Here I'd have 5.5 times 125. Here I'd have 5.5 times 125. So as long as you're consistent, and that reciprocal rule also tells us that, that's what this kind of is. I could flip them. I could put shadows over heights. Lots of different choices. You just have to stay consistent. That's the key. All right, so let's go ahead and multiply this. We get 6.5x is going to equal 5.5 times 125, which is 687.5. And then I divide both sides by 6.5, and I get that the flagpole is approximately 105.769. So 769, we're going to round to 0.8, and that's feet. Okay, it should be taller than the human. It should be shorter than its shadow if we're going to be consistent with our proportions. All right, so this slide is talking about how angle similarity theorem is what we used in that previous problem. How do we know that those triangles are similar? Because not all triangles are. We can't show all angles congruent and all sides proportional. We didn't have all that information. So therefore, we need a few new theorems. And the first one is angle-angle similarity. If two triangles have two pairs of congruent angles, then the triangles are similar. So I kind of jumped the gun yet again with that, and I used angle-angle and I talked about it, when technically this is our first exposure to it. Okay, so angle-angle similarity theorem is our first way to prove triangles are similar. All right, our next theorem about similarity and how we could tell if triangles are similar is side-side-side similarity theorem. If two triangles have all three pairs of corresponding sides that are proportional, then they're similar. You don't have to know the angle measures, but you do have to show that the ratio of corresponding sides are equal. So if I was to do that here, if I start with this yellow triangle, I could start with 6, 7.5, or 12. That's totally my prerogative. I could choose whichever side I want. So if I choose 6, whoops, I did not want to make that a highlighter, sorry. If I choose 6, how do I know what side it corresponds to of the little blue triangle? Well, I look at 6 and I think, okay, is this the shortest, longest, or medium side of this triangle? 6, 7.5, and 12, it's the shortest. So if I'm going to compare it to anything in the blue triangle, it's going to be to 2, because 2 is the shortest side. Then I'm checking, is this equal to? And I'll just go in order. So I'll take the medium side, 7.5 over 2.5. And then longest side, 12, to longest side, 4. Now all of these reduce to 3, 3, and 3. So therefore, this is a 3-to-1 similarity, but they equal, and I'll put the ones there. So they equal each other, therefore I would know that these two triangles are in fact similar. All right, last theorem here today for triangle similarity and side-angle-side theorem. If you have two triangles, if they have two pairs of corresponding sides that are proportional, so like we have 12, 9, 4, and 3, and then the included angle. The included angle is the one between them that is being formed by those two sides. So that's why it's side, angle, and then a side. Same thing here. Side, angle, side. So the angles congruent. Sides have to be proportional. Well, 67 is congruent to 67, so now I'm going to check. Is 12, the longer side of the pink triangle, over 4, the longer side of the green triangle, equal to 9, short side to short side? Well, again, we get a 3-to-1. That's not always going to happen. It just happens to be in these two examples. You could have like 7-to-4, 3-to-8, it just depends. It's not always 3-to-1. This is just a coincidence. All right, this last one is actually one of my favorite triangle type of problems, because we have to focus, in this picture, we have to focus on the two triangles that we have. And a lot of times kids focus on this quadrilateral, and that's not what we want to do. We want to focus on our two triangles. So I say, whenever you have an overlap like this, any kind of overlap, it's safe to redraw the triangles. So if I have N, I'm doing the top one, NMP. This side is 10, this side is 12, I don't know NP. Then my big triangle, all right? Because a lot of times kids will take 15. That is not the side of a triangle. That is not the entire side of the triangle, it's a piece of it. So the entire side of the triangle is adding up those two, and we would get 25. Same thing on the right side. 18 is not the side of a triangle, it's the side of what looks like a trapezoid here. We're gonna add these two together and we get 30. So this is RMS. All right, so we have three similarity theorems. Angle, angle. Well, I don't have two angles here. Side, side, side. If you look at these two triangles I drew, I don't have the third side. I don't have NP, I don't have RS. So the last one is side, then an angle, then a side. And this one again is a little bit tricky. What you have to notice is they share that that angle M. So we do have side, angle, side. I don't know what angle M is. I have no idea how big it is, but I do know that it's going to be congruent amongst these two triangles because they both have that angle as a vertex. So to check if they're similar, I'm going to take 10, the shorter side of my little triangle, the top part, over 25, and we're going to see, does this equal 12 over 30? Well, when you just look at this, you might think, I don't know. These numbers don't look the same. You have two options. You could either cross multiply and see if you get the same products, or just reduce. 10 and 25 both have a 5 in common, so that's 2/5. 12 and 30 both have a 6 in common. So if I divide 12 by 6, I get 2. If I divide 30 by 6, I get 5. So therefore, Yes, the triangles are similar. I'm going to check in a second if we had to write a similarity statement. So I'm going to zoom back up. And they did not ask me that, but they did say, if so, how long is NP? So we are looking for side NP. And just as I said that, I realized I didn't label this side. Okay, so that's 20. Otherwise, I would not be able to do this problem. So I thought, uh-oh. Okay, so let's call NP X. If I'm looking for X, I have many choices of how I could set up a proportion here. For example, I could take my triangle on the right and say 10, the left side, over the bottom, X, is going to equal, now I have to stay consistent for the triangle on the right. So if I took 10, which side corresponds to 10? 10 is the shorter side, so it's going to be 25. Over the bottom, which is 20. Okay, I could have written something totally different. I could have written X over 12. So the triangle on the left, I took the bottom over the right side, equals the bottom over the right side. Notice when I cross multiply, here I would get 25x equals 200. So x is going to equal 8. Okay, NP is 8. If I did it on this side, I get 30x equals 240. Divide by 30, I get x equals 8. So as long as you're consistent, there are many different ways you could write these proportions. There's not just one set way that you have to think like, oh my gosh, I gotta memorize this. This is the only way to do it. Consistency here is the key to these problems. All right, that's it for this homework. I see these books made their way to the last page that you had in that wagon, so get to work on your homework. All right, thank you so much for watching. Have a great day. Bye.